We start New Manufacturing Seminar, the Machine Tool Covers version. This is a 15 minutes introduction video. Let's begin. In recent years, round shapes and obtuse angles are being heavily used for the design cover of machine tools. However, high skills are required to manufacture covers with both great design and function. So from workload perspectives, the manufacturer is being asked to cut costs while workload is increasing. Coming up with simple and quick error-free manufacturing without depending on skills, while reducing costs, has become an important issue. Today, we use Amada's Turning Center S10 cover to propose our new efficient methods that reduce manufacturing lead time by focusing on the manufacturer's and supplier's key themes: skill-free and cost reduction. Let us introduce specific new manufacturing examples with the 4 parts used in this S10 cover. The 3 points are: 1. Process reduction, 2. Improved bending process, and 3. Improved welding process. First point is lead time reduction through process reduction. Weld nuts are widely used for machine tool covers. This product needs 136 weld nuts as instructed. On the shop floor, it is done manually, which takes time, and mistakes such as missing welds and wrong size can easily happen. In the new proposal, we are replacing weld nuts for extrusion and tapping. The manufacturing lead time is reduced by automated blanking process. Since 16.4 kilonewtons, tensile strength is verified in test for mild steel of 2.3 mm thickness M6. Extrusion tapping process is an effective method for cost reduction unless otherwise specified. Also, extrusion on 2 mm thickness of stainless used to be difficult, but it now has been made possible with the improved leading-edge forged extrusion technology. It has 10.1 kilonewtons tensile strength, sufficient for general use. Forged extrusion is a technology that potentiates extrusion on thick materials. The forged extrusion consists of 3 steps. Unlike the traditional method, forming is done first before punching, which makes the processing stable even for thick sheets. Using animation, this is how it is processed. The first process is forming with the forged extrusion tool. The second process is punching with another special forged extrusion tool to complete the extrusion shape. The third process is tapping to complete the forged extrusion tap. Next, this reinforcement part requires chamfering to avoid collision with the inside R of a bend. Chamfering is generally done after blanking by machine or by hand. Here, chamfering is done simultaneously in the automated blanking process to reduce total lead time. The order of chamfering is 1. Relief hole, 2. Chamfering, 3. Finishing process, in these 3 steps. The first process is cutting a relief hole with a laser. The second process is forming with chamfering tool. The third process is punching with the die to complete the chamfering process. 3mm pitch fitting is possible, so processing length can be set flexibly by the program. The range of chamfering may be changed by adjusting the machine's press stroke, so it can be used for a wide range of products. The maximum amount of chamfering varies by material thickness or material itself, but it can accommodate up to around 60%. Next, let us introduce the features that realize bending efficiency. In recent years, the machine cover design has greatly improved, and the parts have become more complicated, so we need various creative ideas to eliminate problems in welding and assembly. Please take a look at this workpiece. If we bend normally without any know-how, the material curls up in this way. This problem occurs unless the material is put on the die shoulder completely. It is difficult to check bending feasibility during the design phase, and in order to process exactly as the design, various creative ideas and know-hows are used. As in the example shown earlier, we avoid the problem by adding a laser slit during the unfolding to the section that does not sit on the die shoulder. Also, diagonal bending is difficult to position and realize stable precision. Here, by adding auxiliary stopper parallel to the bend line, we can bend with a stable precision. By adding half-share joints to the auxiliary stopper, we can use sufficient strength during bending, and it can be cut off easily after the bending process. This is the picture of what you have just seen in computer graphics. You can cut it off easily by hand, so it is very effective in realizing total lead time reduction. Next, let us introduce you the improvements in welding process. For the welding process, it takes a lot of time for workpiece positioning, checking the weld spots, and with the setups. In order to reduce these setups, we place laser marking to show the weld spots, and add positioning tabs during programming. When welding line is to be R-shaped, sufficient 50-50 weld overlap is in need. This positioning is very difficult. As an effective positioning method, tab and slot design at the half of the thickness of the material is provided. Tabs and slots are made during the blanking process. They are processed in 3 steps, in this order. 1. Square hole processing, 2. Pressing, and 3. Laser cutting. The first step is making a square hole. Second process is pressing with a special tool. The square hole in the first process is made to avoid the material from deforming during the pressing process. The third process is cutting the profile into tab shape with a laser. This part requires welding on the ends after bending. The problem of welding with this part is the swelling of the bended edges. The welded portion does not stick well due to the swelling, and it produces defects from slanting welded parts or a gap between welded portion. So it requires an additional operation of removing the swells with grinding before welding. To solve this problem, we have added a slit to the end of bend line that takes into account the swelling after bending. This will eliminate the swelling removal work and can go on to the welding right after bending. Please take a look at this workpiece. It has many welding areas, and it can easily be distorted by positioning error or by heat effect, and it requires very high welding skills. Holes on the back surface and half shear near the welding section are added for fit structure. This allows to position with better precision and can prevent misalignment during tack welding, improving the overall precision. Finishing processes are necessary after general welding, such as TIG. By replacing this with the latest fiber laser welding, the high-grade welding can be done with reduction of finishing process, leading to overall lead time reduction. Finally, we would like to introduce our latest blanking, bending, and welding solution best suited for the new manufacturing, for efficiently incorporating processing know-how we have shown you so far. Akius, the punching and laser combination machine, is for integrating multiple processes into the blanking process and realizes high-grade automation. HG, the high-accuracy, eco-friendly press brake, is for realizing high productivity for complicated shapes and R bends. FLW, the fiber laser welding solution, is the high-grade welding machine challenging the boundaries of welding. We have introduced our latest processing technologies and solutions that realize new manufacturing. Amada has been working on a system to reduce the lead time of high-value added products without depending on the skills. Amada's new manufacturing will drastically change sheet metal processing. We will continue to work with customers in solving manufacturing issues. Thanks for your audience.